over the answers to Q1, Q-2-1, energy, work, and heat. You can check out the score here, 75%. Not our best work, but not our worst either. I think we've had some worse than that. If we break it down by section, first period came in at 77, second period came in at 68, third period came in at 79. Third period must be the Smarties again. Go back to all sections here. So if you're probably in here, one thing I want to say right off the bat is I did make this out of 23 rather than 25. There's one question toward the end where you'll see things didn't go maybe as well as we had hoped. So just something to think about here. It could definitely help your grade if you get a 20 out of 23. First question, first multiple choice question. Work done accelerating an object along a frictionless horizontal surface is equal to the change in the object's what? Right from the review, right? See the high percentage? Right from the review. Kinetic energy. It's a little weird because the numbers are scrambled. But hopefully that wasn't an issue. It looks like maybe 3 of you might have fallen for that. Person weighing 600 newtons, another one right from the review, rides up an elevator. Average speed of 3 for 5, that's 15 meters. So 600 times 15, 9,000. So 95% correct on that. 2 students of equal weights go from the first floor to the second floor. The first student uses an elevator. The second student walks up the flight of stairs. Compare the gravitational potential energy gained by the first student. The gravitational potential energy gained by the second student is the same. Makes no difference. Now, they would have different powers. The reason they would have different powers is because it took different amounts of time. The rate of work would be different, but the works themselves are the same. Which equation can be used to solve for velocity of a falling object? Right from our flex book, we derived this. We set potential equal to kinetic. We canceled out the masses. We solved for V. This is what you get, square root 2GH. We use that right from the roller coaster problem on the flex. True or false? Kinetic energy is the form of mechanical energy which depends upon position. Definitely false. It depends upon speed. This is shocking to me. Shocking. 65%. Come on. 2,500 calories of heat is how many food calories? 2.5 food calories. Divide by 1,000. There's 1,000 heat calories in a food calorie. Here's another one. MA. MA stands for mechanical advantage on the board. If you look up, you'll see there's a comparison of forces, and that's the right answer. Forces, 56%. It's right on the board. Here's a trick question. Look at the percentage, 48. 10 kilogram mass is held 1 meter above the table for 25 seconds. How much work is done? None. You have to have distance. No distance, no work. Remember wall sits? They're awful, but no work is being done. Don't confuse trying and difficult with actual work. Okay, skipping the piano problem, skipping specific heat. All right, so here we go. Back to more multiple guess. Here we have an object. We're going to lift it 10 meters. Realize if you do it at a diagonal, you still lift it 10 meters. So it's kind of a trick question. If it's 100 joules to go from A to B, that means that it would be 100 joules to go from A to C because the heights are the same. 50%, kind of tricky. Which of the following units are equivalent to a joule? Now there's only 3 because joule is not there. Only 2. Next, amount of heat required to raise the temperature of an object by 1 degree is called its specific heat. Look at that. Great job. The work done on a slingshot is 40 joules to pull back. That's potential energy. If the slingshot projects the stone straight up in the air, to what maximum height would the stone rise? This is very similar to the very tricky one at the end, but we did much better on this, so I'm not really sure why. So set 40 equal to mgh. 0.1 times 9.8 is 1. So the weight is 1, 40, and then you can solve for the height. So the height would be 41, 76%. Here's the wax pellets right from the review. We know it's 3 only. All right, so let's get into some of the trig and runaway object problem. So this time around, we're talking about this piano. This is a piano with a mass of 200 slides out the back of a moving truck. Jimmy stops the piano by exerting a force of 45 at an angle of 30 below the horizontal. He pushes 12 meters on a surface with a coefficient of friction of 0.15. So we start by calculating normal force. So I'm going to just pull up a calculator here so we can see how this is going to work. So first thing, check your mode. Okay, what mode am I in? I am in radian. See, that would be a problem. Move over to degree, press enter. Then, now that I'm in degrees, I'm ready to roll. All right, so I don't have the problem out in front of me, so maybe best to shrink the screens here if I know how to do this. All right, that's about as good as I can do, I think. Okay, so let's start by finding the weight, and then we'll add in the y component. So 200 times 9.8. So that's the weight, FMG, and then 30 degrees is my angle with 45 newtons. So I have to add, to get the normal force, I have to take the hypotenuse and multiply by the sine of the angle. My angle this time was 30 degrees. 45 sine 30. So there we go. 1982.5. You see that fits in between this range nicely. 83% of us were able to do that. Now that we have the normal force and we have the coefficient of friction, I can just multiply these two things. So when I multiply, you can see I'm getting a friction of around 300. It's actually negative, so I have a negative answer in there, but only one person took the time to make it negative. Just curious who that was, but I'll check later. All right, so then if we want to get the acceleration, we have to add in the x component here. So if this is my friction, to that, what I want to do is take 45 cosine of the angle 30 and add it to it. So here's my net force, the net force being 336. Now that's not my answer. I have to divide by the mass, 200. So then I come over here and divide by 200. Doing so gives me 1.6, but remember it's negative, so most people did that, but 2 people, I left the positive answer just in case. So that's about 73% correct. 3/4 of you could come up with the acceleration. That's not bad. That's the old way. What about the new way? So we go back to our number, 336. See if I can get the change here. 0.34, and I multiply by the distance. So the distance we moved was 12. So I just multiply by 12 here, and I get 4,036. You can see that puts me in my range as well for the network. Now you can use either way, old way or new way, and you can solve for the velocity. So let's talk about what we do with this 4036 number. So 4036 is the work. That's equal to force times distance. It also equals a change in energy, and the type of energy is kinetic. Now, considering we get to a point where it's at rest, the final velocity cancels, and then ignore the negative sign because it's a scalar, 1/2 mv squared. So 4036 is going to be equal to 1/2 the mass, 200, times the velocity squared. So that's 100. That's easy to work with. So if we divide by 100 here, okay, move the decimal over 2 places. You got 4036 equals v squared. Now I'm ready to kind of work through this a little bit. And square root. So it looks like we're getting about 6.4. Let's see how that falls on my range here. Yep, between 6.2 and 6.45. So that's how fast it was going when we jumped in front of it. Now you could do it the other way too. So I could go back here to my acceleration. So my acceleration that I had, let's see if we can move up through the calculator here. See what the acceleration was. Negative 1.68. So if I take negative 1.68 and then I plug it into magic physics formula number 4, which looks like this. Okay, gotta get all my numbers. We want to know what this is. This is 0, 2 times, this is where that number comes in, negative 1.68. We got distance. My distance here, I've already forgotten. 12 starts at 0. So here we go. We're going to take the negative times 2 and times 12. don't know if you can see that. Yeah, I guess you can. Okay, now that we're going to get rid of that negative number by moving it across to the other side, and then we're going to square root. You'll see you get the same answer, which is always the goal. What we had last time, 6.4, 6.34, that's basically 6.4. You'll see both of them fit within the range though. Look at that. Okay, so that's the long one. 65%, I'll take it. It's not too bad. All right, how about the Q stuff here? So when we talk about Q, we have to fill in our chart. So let me just whip up one of these charts real quick. I think adding the little stuff on the end of the chart really does make life a little bit better for you. So I would highly recommend having everything that you see there and then just adding a little bit more. So we have the Q equation like this. And then off the end, we're going to put EQ, and we're going to put some parentheses. So these are initial temperatures, and these are final temperatures. Now I'm going to read through the problem, and we'll fill in the chart, and I'll bring it back here. So we have 100 grams for the metal. So I'll put 100 in here. Remember, we don't know what the specific heat is. It's originally in boiling water. Then the metal is transferred to 200 milliliters of water in the calorimeter. Specific heat of water is 1. At 23, that's the initial. Afterwards, it's 25. So this went up 2 and this went down 75. Okay, so 2 times 200 is 400 joules. And then we divide it by 175. So 400 divided by 100 divided by 75. That gives me roughly 0.053, which I think was tin's specific heat, if I remember right, from our lab. Let's see. Q has to be right in between these numbers. 400 gets the job done. Then we kind of go down and we look at what the specific heat was. That fits in that range nicely. Okay, last but not least, we have this problem that we struggled with. The reason we're struggling with this is because we have to go back. We have to go back to where we had Q. Okay, so we're talking about this. Q, 400 calories. So right off the bat, what you want to do with the 400 number is you want to multiply it by 4.18. That's going to turn it into joules, and this is the number one problem, I think. 1672 is thermal energy, which is work. 1672. That's going to be equal to a change potential energy, which is mgh. And we can solve for how high we can lift it. You could also say force times distance, where mg would be force. Now it's a 22 kilogram block. Multiply that by 9.8 is 215.6. So if I take the answer in my calculator and I divide by 215.6, you can see I end up with 7.7 meters. So it wasn't really maybe as hard as you thought, but I imagine most people forgot to go from calories to joules. That puts me in the range nicely. Okay, so retake is up and available. I'm going to go ahead and unlock it right now. I'm going to walk you through that so you can see that I'm actually doing it and where to find the retake. So we'll click modules here. Come on, BHS. Well, I had hoped. Oh, there we go. Let's go down here to, oh, this is all the new stuff. There we go, retake. And I'm going to go ahead and unlock it. Now, as I kind of